Welcome back to HVAC-Engineering-Techie. This is the channel where we talk all things HVAC. We discuss engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature to help you advance your career, and they will certainly do that. Today's lesson is on air-water system diversity. This is another video in the tab series that deals with system balancing, not just how you do one thing, but how you do a whole system. And today it's just a piece of a system, how to do diversity. So variable volume systems can have diversity. And this is a subject that messes up a lot of balance, guys. So it's one I paid a little attention to. That's why I made it a separate section. So before we do, I'd like to ask you a big favor. If you're not already a subscribing member, would you please become a subscribing member by hitting the subscribe button and the thumbs up button down below? It's absolutely free. It costs you absolutely nothing. But it really helps me because Google uses this to value this video. So it would really help me if you do that. And so let's get started. So what is diversity? That's the first thing we need to figure out. Diversity is the difference between the total of the zone loads to the load of the main unit. So when an engineer designs a job, he normally does his calculations by zone, so he can figure out how much load he needs to take care of in a certain zone. And then he may do an entire block load, which would be all the zones together. And that may be actually a different load. And so the diversity comes in when he has more zone load than he has main load, and that's what diversity is. Diversity happens both for VAV air systems and can happen for variable flow water systems. It's more unusual for chill water system to have diversity, but not impossible. So those two can possibly have it. So why do systems have diversity? Why is zone load different than block load? Should they be the same? Well, actually, for air conditioning, for cooling, it is not. So designers calculate the zone load for each room, just like I said. The reason it changes is because the solar load is not consistent on each face of the building through the whole day, right? So here's a building, and it's sitting somewhere, and you notice this is the east side, and this is the west side. And in the morning, the sun comes up in the east side and heats the east side and moves around to the west side. So each zone, so the east zone is warmer in the morning, west zone is warmer in the afternoon, and the south zone sees the sun from transition from morning to afternoon. So that's why he can use diversity, because there's never a time when the whole building will see 100% design load of all hours of the day, because the sun moves around. And that's why we get diversity. Now the perimeter load is worth 20-25% of the total load. And that's just the way it is. When you do a design, you'll figure that out. So basically, our diversity should be in that range. We should be 70-75% maximum. If you get below that, now you're actually have some internal load that's going to be in diversity, which is not good. That could hurt you. So other systems that have diversity, now there are some other ways that you can have diversity of building besides the sun load, but diversity may also result from large internal loads that move around the building as long as they never happen at the same time. Maybe you have a manufacturing plant where the whole crew moves from station to station or something. It's possible. It's unusual, but it is possible. Also, another one that I've run into is campus systems may have diversity load due to building loads being timed differently between buildings. So if you have a campus and for some strange reason one is building is open at night and the rest aren't, or some other circumstance that leaves them unoccupied, the total plant, the central plant that runs many buildings, may actually have diversity. So this is the air diversity system. This system has an air handler that feeds two areas, an A area and a B area. And it's got a VFD, and it's just a normal system. And here's the A boxes and the B boxes, and here's their design load. And it comes up to 16,170 CFM. But this air handler is designed for 12,700. So that's how we know it has diversity, because we added up all the boxes and they don't equal this. Now, if the air handler is larger or equal, then we don't have diversity. And so we balance it slightly different. It's similar, but it's slightly different. And the session on VAV balancing will cover that. And but this is strictly for systems with diversity. So we have 16,170 CFM, and that the diversity is 78.54%. And the shortfall is 3,470 CFM, or 21%. So you can see we're in that 20 to 25% exterior load. So now what we have to do, what are we trying to do when we balance diversity? Well, we're basically trying to turn it into a constant volume system. We want a solid amount of air from the air handler, a block of air, and we want that evenly distributed to the boxes into zones. So that way we can guarantee that if you have a design load everywhere in the building, this air handler will actually provide enough air, and those boxes are balanced and the grills are balanced so that they will all get 100% air. So to do that, we have to reduce the air on some of these boxes to be able to get the air load in the field to equal this 12,700. So that's what we're going to do. We're going to set it up so that the air handler sets out a fixed flow, and the boxes we're balancing are going to be equal to that fixed flow. That's the basic. Now, the details are devil's in the details, right? Well, that's what we're going to talk about now, is the details. So in this example, the total is 16,170 of the VAV boxes. We divide by one of the other, and the formula is air handler CFM divided by total box CFM equals percent diversity. In this case, it's 12,700 over 16,170, which equals 78.5% diversity. Determine if this percent diversity is within the normal diversity range, which is 70 to 100%. And that's a rule of thumb, so it's not cast in stone anywhere. But if you have a job that's 59%, it's got a big problem. Something's drastically wrong. And the only places I've seen that sometimes is when they are converting a system from one kind to another. Like I've seen them, the buildings were originally built for cold water, for ice systems that had 38-degree water circulating. And they switched them to, because those systems were problematic to maintain, they switched it to a normal central plant. And the problem is now the diversity is really different. And so I've seen diversity as low as 58%. Didn't work, but I've seen that. And so you have to make sure. And what happens if you have a lower diversity than 70? Just simply ask the engineer, is this okay? I noticed the diversity is 70%. It's below 70%. I just don't want there to be a problem. You're sure this is okay? And then if he says, yep, that's exactly what I want, that's not your decision. Then you move on and do that lower diversity. So balancing VAV air handler systems with diversity, how do we do that? Okay, first we calculate the diversity, which we've already done. Then verify all grills downstream of the VAV terminal units are all 100% open and the air handler has clean filters. So now we're guaranteeing, they're all open so we can see total flow. Then you close off the boxes equal to diversity flow amount, commanding the dampers 100% closed. Okay, so we went through and I selected box A2, A5, B1, B7, and B5 to close. Now what we're going to do is we're going to close these boxes to get down somewhere near that 12,700 CFM. We didn't quite make it, but we're close. And we're going to use those boxes. We're going to close those first, and then we're going to balance these other boxes. And then we'll come back and open these boxes and close other boxes. Now let's read it to make sure we get everything else. Close off boxes equal to diversity flow amount by commanding the damper 100% closed. Always close slightly more CFM to ensure you are balancing at a slightly lower diversity. Or set the air handler unit to slightly more CFM than full design. So what we want is we need a few CFM to play around with because we're going to start back pressuring the system as we start to balance boxes. So it's always better to have a few to start with. If not, we'll have to deal with it later. So then after that, it's once we've got these boxes closed, these ones I show here closed, in software set all of the boxes to 100% open damper position. Now I've seen guys try to do this a lot of other ways, like set the thermostat, the room sensor down to 55 degrees, 58 degrees, and then take the air handler temperature and raise it up to 75, and all the dampers will go open. But that might be dangerous if there's a condition changes somewhere. Because remember, we want this to be a constant volume system we're balancing, not a variable volume system. So we want this air handler locked in position, and we want these boxes locked in position. And to do that is command the software to just drive the damper 100% open. It knows where that is, and it will do that. It's the safest way to do it. It's probably the fastest way, because running around setting all the room sensors takes some time. If you have a good programmer on your system, should be able to do this with a global command. Command all boxes open. Now, that you might have to do that first and then close the ones you want 100% closed later. But whatever you have to do, whether you have to do them one at a time, you need them 100% closed. Lock the air handler flow to diversity design flow by manually setting the supply and return fan speed at the VFD. So what you're going to do is you're going to take the fans out of automatic control. And you're going to verify that by a pitot or by a fan curve. Some way you're going to verify what your flow actually is, because you need it to make sure that it's that 12,700. That's what you want, or maybe 12,750 or something like that. You want it higher. In this case, since my balance selection I picked was, I don't remember, I can't see what it is, 12,720. So we need to add a few more CFM, maybe kick it up to 12,800 or something like that, so you have some more flow. Take preliminary balance readings for each box. So you're going to run around your building, and this doesn't take very long. A lot of guys are growing at this, but it doesn't take long. And you're just going to take a reading on all your grills per box. Add them up. That's your box flow, and then you're going to list those. You're going to begin balancing. You're going to list those from the highest percentage flow to the lowest percentage flow. And this is your preliminary reads. So this is a preliminary reading, and that's what they're going to be. Now, these are all made up, of course, so they may be drastically different than I have here. Begin balancing boxes from the highest percentage flow to the lowest percentage flow. Balance all box grills by either a series or proportional balance. See sessions T7 for proportional balance, how you do that. Once a box is calibrated, leave it automatically tracking the design maximum flow. So once you've done balancing the box, you balance the box, and you know where that damper position needs to be, okay? So you calibrate the box, and you put the calibration of the box, and you have to read the manufacturer's literature for that, because every box manufacturer does that slightly different. But once you have the box calibrated, and remember that calibration of that basically tells the box, okay, damper full open, we have 1,000 CFM, and he balanced it, and he wants 850 CFM. So it tells the box that full open position should be 850 CFM, and it knows where that is. So it calibrates the velocity pressure input signal to what the maximum flow of that box needs to be. So once it's calibrated, then you simply change the box from being full open. Your command was full open. Now you turn it to automatic control, but you want it to maintain that maximum box damper position. So now the pitot will still move the damper up and down to change pressure, but you want it to maintain that flow. So you want to put it in, you want to override the box to a certain CFM level, which is the balance level. We're doing that because we want it to stay constant. No matter what we do with it upstream, we want it to have design flow. Because remember, air handler is locked at design flow, and we want the boxes to remain at design flow. So if you run low on supply air as you balance the last few boxes due to increased system static pressure, then go back and recheck the supply of fan flow. And if it's low, increase the fan speed to back up to where it needs to be to give you that flow you wanted. If the fan is already at maximum speed, then recheck your diversity calculation and setup. Something's wrong. It can't be, right? So either you made a mistake somewhere, or something didn't work on another box or something. Something's wrong. You need to figure that out. Complete balancing and calibrating all diversity flow boxes. So all the boxes that you didn't close, you finish balancing all those. So once you're balancing and calibrating all of those, you remeasure the supply air deck static pressure. Now remember, we never put a static pressure set point in, right? Because we're not using it. We lock the fan by manually by inputting the keypad on the VFD to a certain speed to get a certain CFM. So it doesn't. We never put one in, but now we're going to read it, And this static pressure will become the final supply air static pressure set point. So that's pretty easy to do. Just you can go ahead and put it in the controller, in the air handler controller now if you want to, or not. You don't need to do it right now, but that is the number you're going to put in as your final set point. So open the closed boxes and close other boxes to equal the diversity flow. So now those we've closed, we're going to open back up and close other boxes so that we have diversity flow again, and then we're going to go balance those boxes that were previously closed. So now we just go back and balance and calibrate those boxes, and we should come up with the same total flow we did before. Now we're done with that. We're done balancing the job, return all the boxes and VFDs to automatic control. Now we just let everything go back to automatic. We're done. Verify the final static pressure set point. Make sure it's programmed in there. Make sure you record that, because that's really important for the owner to know what that is. And that's basically how you balance a VAV air handler with diversity. It's not difficult, but where people get messed up is they try to leave the air handler in automatic static pressure control. That will not work, because it will vary, and that's not what we're trying to do. We're trying to guarantee that the design CFM of the air handler will provide designed air at all the boxes at the same time. That's our maximum flow deal. And if you leave it in automatic, it won't work. You can't do that. So that's where people get messed up trying to figure that out, and that just won't work. Okay, so balancing a VAV chill water system. Okay, chill water systems can have diversity. It's not as common as air system, but it is possible, because they could have a bunch of fan coils out in spaces, and they could have diversity load just like that air system could. So here we have a small system. It has only 7 fan coil units, and they total up to 400 GPM. But there's 2 300 GPM pumps. This is one of my pet peeves, but I don't get very far, is why designers don't tell us how many pumps are supposed to run. They never do. So basically the pumps are 300, and this is the total of the coils is 400. So if you divide the one by the other, you get a diversity of 75%. So our shortfall is 100 GPM. So somehow we have to figure this out. So first thing, add up all the design GPMs from all connected coils. In this example, the total is 400 GPM. Determine how many pumps are supposed to be operating for the load. This you got to figure out, because no one's going to tell you. The drawings don't tell you. There's a hint in the control sequence. You want to go read the sequence, but even that, you need to test a couple of other things. Normally, you would assume with this job it has 2 pumps. One is lead and one is standby for backup. That's the way it actually should be, but this may not be the case. Sometimes engineers decide that they can get by with no standby or 50% load standby in case a pump fails. But here's how to test. If the pipe is sized for double the flow, so if the pipe is sized for 600 GPM, then you know, and the coils have, and all the coil is over twice one pump, then both pumps are required to run. Now it might be 1.5 or so, but this is a little low. This is only 400 GPM. So if it was 500 GPM, then it would definitely be a two pump run job. So I'm assuming that this one really is a chill water system with diversity. And that's what we're trying to make sure we know how to do that. Divide the total design GPM of the pump with a coil total load, which equals the percent diversity. Again, pump GPM over total coil GPM equals diversity. In this case, 300 over 400 equals 75% diversity. Determine if this diversity is within the normal diversity range, 75% to 100%. Again, that's a rule of thumb that is just experience-based. Normally, I like to see in between 80 and 100, but depending on the building and how well it's built, you could have a smaller one. If the diversity is below 75%, question if this was the intended design diversity. A phone call to the designer is no problem. A designer's willing to help you. You're balancing his job, and you're making him look good. So if the building doesn't work correctly, people are uncomfortable. He's not happy. He shouldn't be happy, because they're going to be upset with him. So basically, you're there to help him, and he should answer your questions. All right, here we go. So how do you balance with chill water flow? It's exactly like the airside system. We want the GPM of the pump to equal the GPM of all the connected coils so we can balance it like a constant volume system. That's what we're trying to do. Verify all shutoff valves, all coil shutoff valves, and balance valves are 100% open. Now, it's pretty easy to tell the shutoff valves are open or closed, but you need to check the balance valves because if they're not closed, it'll mess you up. And all the strainers have been cleaned and the startup mesh strainers have been removed. And remember, in water systems, many times the larger strainers will have a sieve that's sized for the pump volute openings, and then they'll have a small screen inside that, which is actually a startup sieve. And that's designed to catch all the rust fines and everything out of the system when they're starting it up and cleaning it. So by the time you get there, those should have been removed because they will put a lot of excess pressure in the system that you don't want. Okay, select coils to close. That will equal or come closest to the pump GPM and override those control valves 100% closed. Best practice is to spread these closed valves throughout the system and not have them all in one area. That's the same with air systems. I may have forgotten to mention that, but we need to distribute them around, and we're just trying not to put them all in one area in case we have a pressure anomaly. We don't want to do that. In software, command all other control valves to 100% open. So here's this system, and I selected 2 and 4 to close, which equals 100 GPM. So this is perfect. This is right on because I set everything at nice round numbers. So now we have the system closed. So now we have the zone load coil should equal the pump flow. That we've got them, they're the same. So lock the pump flow to diversity design flow by manually setting the pump VFD at this speed at the VFD. Flow verified by pump curves. So now you're going to set that up and lock it in its speed. Take preliminary balance valve readings for each coil, listing them from the highest percentage flow to the lowest percentage flow. So we've done that here. We've got the highest here, which is number 7, and we go to the lowest here. Now remember, these are all over the building, right? We don't do it in order. We don't do rooms in order. We do it by percentage flow in order. Begin balancing each coil balance valve starting at the highest percentage coil to the lowest percentage coil. If the few lower coils do not have enough water flow due to increased system pressure, increase the pump speed until the lowest coil has adequate flow overflow. If the pump is already at maximum speed, then recheck your diversity calculations and setup. Now, normally VFD pumps are run to 60 hertz to full speed. Hopefully the pump's not a 3,600 RPM speed pump. But if the pump's a normal 1,800 or 1,750 RPM pump, you can actually speed it up beyond 60 hertz. If you need just a few more GPM, you can run it at, instead of 60, you can run at 65% without a problem. Pumps will do that, and the VFD will do that without a problem. Now, you may have to have someone help you do that. You may have to go into the software setup to allow it to go beyond 60 hertz. But you can do that if you have to. So complete balancing all diversity flow valves. So now you're going to balance all the valves that you have open, that have been commanded open. Remeasure the pipe system differential pressure. This will be the final differential pressure set point. Now remember, we didn't set the differential pressure. We locked the pumps in flow. So now that we've finished balancing all those that aren't closed, now that will be our final differential pressure set point. Open the closed control valves that were closed to simulate the diversity and close other coils to simulate the diversity and balance those coils. Balance coils that were previously closed. Record the chill water supply or your water system differential pressure set point. Once you finish balancing the system, up here we determined what it was when we did the first pass. So now here, we're going to take that value and program it into the system. So record that differential set point, put it into the system. We're going to release all valves, override positions to automatic control, and release the differential pressure set point to automatic control, and also release the automatic reset sequence. So that basically is how you do the chill water system. Now, what about a hot water flow system? Well, building hot water heating systems normally do not have any diversity because when it's cold and cloudy, there's no sun load and moves around the building, causing diversity. So basically, there's no diversity in the hot water system. If you have diversity, you need to think hard and long about this. Why does it have diversity? It's possible to have diversity in a hot water system that has the following conditions: internal loads that change and move around the building and never exist at the same time. Process could do that. Loads that are time dependent, such as morning warm-up. Now, I have found that where we have hot water coils in the air handlers for morning warm-up, and then we have reheat coils out in the space. So you have to switch between those two. They don't get it all. It's not truly diversity, but you have to think about it when you can. So basically, if your hot water system has diversity, you need to ask the engineer, are you sure you have diversity? And if he says or doesn't answer, I mean, a lot of times I found this is due to mistakes. Somehow or the other during the process of the job, changes were made and they weren't picked up in the schedule of either the coils or of the pump, because there really shouldn't be any. The diversity should be the same. And one thing about hot water systems is good to check. Does the pumps match the boiler flow? Does the pump flow match boiler flow? Does it match coil flow? And that's how you'll tell, because I've seen jobs where the pumps don't match the boilers don't match the coils, and the coils don't match either one of those, which means that was design error, and that should be looked into by the designer. Well, that's diversity. I hope that was comfortable and you understand what we're doing there. It's really important that you know how to do diversity setup and how to do diversity balance. Once you fully understand it, it's not hard. It doesn't take a lot of time. You can run right through it, but you have to get it correct in your mind first. So appreciate you being a subscribing member. If you're not, please do so. That would be greatly appreciated. You guys have a great day, and I'll catch you on the next one.